final part of the session, Introduction to Chemistry of the Environment, we are going to be looking at how chemistry and chemical processes underpin some of the changes that occur and some of the interactions that occur between the four spheres of Earth: the biosphere, the geosphere, the hydrosphere, and the atmosphere. The changes that occur in energy and matter within each of the spheres and between the spheres, between the different environmental systems, are sometimes physical in nature, but in many cases chemical. And in order to understand those processes, we're going to have to dig a bit into the chemical structure of the compounds. What's happening when those reactions happen, when those reactions are taking place at a molecular level, at an atomic level, looking at the chemical compounds. And throughout this video, I'm going to ask you several times, you pause the video and you analyze the graph I'm presenting you, and that you discuss it and take some notes. And I would really, really encourage you to do it. Pausing the video, trying to analyze the figure I'm going to show to you, trying to extract as much information as you can, and only then hitting play and seeing what my explanation, my take on the figure is. And only then you will really start to develop your skills, your understanding as an environmental chemist, which is what you are doing on this module. So we have here a diagram of what we call species distribution. This is something we're going to be studying in this module in quite a lot of detail. And when I talk about the species, I don't mean animals or plants. What I mean is chemical species, compounds, atoms, elements are in different, depending on where they are, whether they're in gas, in the atmosphere, or the biosphere, or the geosphere, or the hydrosphere, they will be in a different form. They will be being part of a different compound. And when we are looking at the species distribution, what we're looking is how the same element appears in different forms depending on whether it is in solid, gas, or liquid form, and also depending on the environmental conditions surrounding it, the temperature, the pH, the presence of other elements surrounding it. So, for example, in this figure, we have here the molecule of CO2 in gas form in the atmosphere. There is an exchange between the CO2 in gas form in the atmosphere and the CO2 present in a water body, let's say an ocean. And so here we've got this same CO2 molecule and in what we call an aqueous form. It's hydrated, it's surrounded by molecules of water. Once it's in, and that's an equilibrium, a certain amount of CO2 stays in gas form, a certain amount of CO2 will be dissolving water, will be in aqueous form, and that is determined by what we call equilibrium constants, and some gases will be more or less soluble in water depending on their structure, and we will look a little bit into those aspects. Once it's in water, the CO2 can react with one molecule of water and form this compound, H2CO3. We call this carbonic acid, or some people just call it CO2 aqueous. So carbonic acid is a very weak acid. And because it has a sort of acidic nature, it's able to donate a hydrogen ion, which is this H+. So it's able to form this intermediate species, this HCO3-. And this HCO3-, we call that the hydrogen carbonate anion. Or you might have heard the old name of hydrogen carbonate, which is bicarbonate. You might be familiar with bicarbonates. Further, along, this molecule of HCO3 minus, it still is slightly acidic, still has this capacity of losing a hydrogen ion, an H+, and can evolve to form the anion carbonate, CO3 minus. And that is still in solution. So the species at the top of this diagram are all dissolved. However, and as you see the double arrows, I mean, all those are equilibrium, depending on the conditions around the temperature, the pressure, the pH. The environmental conditions will determine if the CO2 molecule is going to be on CO2 hydrated form, or in the form of carbonic acid, or in the form of hydrogen carbonate, or in the form of carbonate. And there will be a certain proportion of all those species at any given time in a water body, and the exact quantity will be determined by the very nature of the species and also the conditions around them, temperature, pressure, etc. So if you imagine your carbonate anion, if there is some calcium ions, calcium 2 plus ions in that ocean, the calcium ions are capable of reacting with the carbonate anions and form calcium carbonate. And calcium carbonate is insoluble and precipitates and can form a mineral structure. For example, is what helps calcify plankton, and it forms it forms a mineral. So then here it's coming out of the solution, it's coming out of the ocean, it's coming out of the water body in a solid state, and because it's coming out of the solid state, is pushing the equilibrium this way. So the more carbonate that reacts with calcium ions, the more hydrogen carbonate that will react to form carbonate, and the more carbonic acid that will react to form hydrogen carbonate, and the more CO2 dissolving water that will evolve to form hydrogen carbonate, are the more CO2 gas that will dissolve in water. So as you can see, the presence of other ions also determine what our molecule, our compound, our atom of interest is, in which form it is. And we will be looking into all this, and we will look at the carbonate species, the equilibria, later on in the module. And you can do this with carbonate species, but also with phosphates, nitrates, sulfates, metal ions, chromium, cadmium, any chemical. Both this type of equilibria happen also in atmosphere. So it is important that we begin to understand how all those different species in which our element can be in, how they are related, and how the certain conditions, certain environmental conditions, will favor some forms of the element and not others. This is a figure that tries to represent what I've just shown you in the previous image as a picture. So I'm going to pause one moment, and I'm going to ask you to pause the video, and I'm going to ask you to look and try to extract as much information about as you can of this graph. So look at things that what are the axes, what are the axes, what are they telling, what sort of units, and also what are they representing, what are the lines, how are the lines related? And see that you have actually three axes. You have a y-axis, and you have slightly two versions of the x-axis. This looking at hydrogen ions, and this one looking at pH. If you feel more comfortable, you might want to focus on the pH one. So pause the video now and spend 3, 4, 5 minutes looking at this graph and writing down, note down anything you can find out about this graph. Hopefully, you have stopped the video as I ask you and try to note down the information that you can see from the graph. And I will tell you what I can see on the graph and how I will ask you to interpret this type of graphs in a few weeks' time when we're studying species distribution. This graph shows the distribution of carbonated species of the chemicals that carbon can be found on in nature as a function of the pH. So here I've got the pH scale from more acidic to more basic. And here I've got what we call the fractional contribution, which is from zero to 1. The proportion of carbon in that particular species, in that particular form at that pH. You can think of it between 0 and 1, or you can think of it between 0 and 100, that's percentage. What is the percentage if you're thinking of 0 to 100? Or what is the proportion if you're thinking between 0 and 1 of carbon in the form of CO2, in the form of HCO3 minus, hydrogen carbonate, in the form of CO3 minus, carbonate. So if, for example, I look at pH 2, it's extremely acidic pH, and at pH 2, all my carbon is going to be in the form of this CO2 aqueous, in this form of CO2 aqueous, which is how some people like to write the acid, carbonic acid. And look, around pH 3 and something, suddenly, well, not all the carbon is going to be in the form of CO2 aqueous. Yes, quite a lot will be, but a very small proportion. This is this is almost 0, and this is 0.001. So we are talking about a very, very small fraction will be in the form of this species, the bicarbonate species, HCO3 minus. And so there will be a very small proportion, and if this graph had better y-axis with more information, we will be able to know the proportion will be in the form of carbonated species, and most of it will be still be in the most acidic form that carbon can appear, which is in the form of carbonic acid or CO2 aqueous. When I'm looking at, for example, pH 5, if you look at pH 5, well, at pH 5, there's actually much more of the proportion of carbon, which will be in the form of bicarbonate, hydrogen carbonate, and still quite a lot again, but much more. Well, much more is 0.1, so it's not. But you know, if we think of we have come from this logarithmic scale, I've never plotted it, so it has increased, but it's still no, you know, like most of it will still be in the form of CO2 aqueous, in the form of carbonic acid. At some point, in a particular point, and we will look at what this point means, is related to the equilibrium constant. Actually, there is the same quantity of carbon in the form of carbonic acid than there is of carbon if in the form of hydrogen carbonate. And that is a specific point and is related to the equilibrium, the acidity constant of that reaction. And when we come to this in the semester, we will study what that point is and how it changes from one species to the other. So if you see when we are at higher pHs, you know, this pH 7 neutral, and slightly we're moving into basic pHs, then things start becoming, well, more interesting, complicated, because you start having another species that appears, this green line, is the carbonated species. So suddenly you have your carbon in three different forms. You have the carbon in the form of carbonic acid. You have a certain amount of carbon, quite a lot actually, which is in the form of hydrogen carbonate, and you have also a certain amount that is in the form of carbonate species. And again, if we had better y-axis, we will be able to see the proportion of each of them on the so how your carbon would it be depending on in this case the pH. At some point, around pH a bit under 9, there's not going to be more carbon in the form of carbonic acid. The pH is too basic. The pH of the water body is too basic for the carbonic acid to still exist, and then you will have still quite a lot of hydrogen carbonate, and a slowly increasing proportion of carbonate ion. Remember again, this is a logarithm scale, so this is 0. Between each of these lines, there is a whole order of magnitude. This is 0.1 and this is 1, so that's a big jump. There is a point here around 9 in which the proportion, there's no more carbonic acid to be seen anywhere. All your carbon will be in the form, half of it in the form of carbonate and the other half in the form of hydrogen carbonate. And again, this particular point is related to the equilibrium constant between those species. And again, when we look at this later in the module, we will be able to understand, hopefully, we will be able to understand why is exactly 9, why 9 and not 10 or 2, and that is because it's related to the acidity constant of those species, of that equilibrium. And finally, when you move to more basic pHs, to 10, 11, 12, etc., then you see that the amount of hydrogen carbonate decreases rapidly, and what you're going to have at a very basic pH will be almost exclusively the carbonate anion. So all this information, which looks rather complicated, and now that I've drawn over the figure, it looks even more complicated. The interesting thing of this is that you do not need to go to a water body and do any analysis to know that. The only thing you need to know is the reactions that carbon experience in water, which is general chemistry knowledge, the equilibrium constant of this species, which is again information that can be found in tabulated data, you can find it in textbooks, etc. And what you do need to know is the water pH, or the pH of your water body. So if you go to a pH meter, if you take a pH meter and go to a water body and measure the pH, and you know that the pH of that water body is, let's say, 12, then you will know that all the carbon that is in that water body will be in the form of carbonated species. If, for example, you measure the pH and the pH is 7, you will be able to know that actually you have 3 different species. The carbon is in that water body. And you will be able to work out the proportions, because this again this is not experimental data. These curves are built with tabulated data you can find in books and databases. So you only need to measure total carbon. For the nitrate, there is a similar graph for phosphate, there is a similar graph for nitrates, and so when you go and measure, you are able to not measure nitrogen in various species, total nitrogen, total phosphorus, total sulfur, total carbon of that water body, and then use this type of curves to work out the individual contribution of the different species. So I hope this was clear, or perhaps it wasn't, but don't worry about it. We will be looking specifically to carbonate equilibria, phosphate equilibria, nitrate equilibria, sulfur equilibria, sulfates. So we will be looking at these graphs in quite a lot of detail in future sessions. I just wanted to advance the sort of graphs we will be looking at throughout this semester. Anthropogenic effects, we will look quite in detail to the effect of human activities on natural processes. And sometimes there are catastrophic events, a disaster, an accident like the Bhopal disaster in India in the mid-1980s, an accidental release of this gas, methyl isocyanate, that create huge impact in human health, and it's still those effects are still seen now, generations after the disaster happened, in the descendants of the people affected. And sometimes you have a more gradual effect, which is more medium and long term, and it tends to be more delocalized. For example, the buildup of greenhouse gases in the atmosphere, and effect in global warming. So we will be both looking at the chemical process in the environment, natural environment, unpolluted environment, and also the effect of human activity in that natural environment, and how it changes the chemistry of the environment. So this is all for this session. I hope it was useful. As always, if you have any questions or comments, please either post in the discussion board for the week or drop me an email. And if you need any help for a specific part that you might need some extra discussion with me, please feel free to organize a tutorial. Thank you very much for listening, and I hope it was useful, and see you soon.